In this lecture, we will introduce the concept of public key encryption. So, public key cryptography started with the Diffie-Hellman key agreement protocol. Essentially, what it means is that two people who are potentially being eavesdropped on an unsecure communication channel would like to exchange information that leads to the creation of a shared private key with which they can encrypt and decrypt communication with, for example, a block cipher type of primitive. So in this setting, we will assume that there are two public parameters, namely P, which is a prime, and G, which is going to be a generator. For example, some number mod P, so for example, G equals 2, okay? Now, Alice and Bob are going to play the following protocol. Alice will choose a secret value A and will create the value capital A, which is G to the A mod P, okay? At the same time, B will choose a secret value B and create capital B, which is G to the B mod P, okay? And now Alice and Bob will exchange this information, which is Alice will send capital A to Bob, while Bob will send capital B to Alice, okay? And at that point, Alice is capable of creating a B to the A mod P, which really is G to the B to the A mod P, which is G to the AB mod P. Meanwhile, Bob is capable of doing the exact opposite operation, which is G to the A to the B mod P, which equals the same thing, G to the AB mod P. Here what's important is that given A and capital B, an adversary is unable to retrieve lowercase a and lowercase b, okay? The hardness of this, this problem, this computational problem of recovering the value small a from capital A and P is called the discrete log problem. So we're relying on the assumption here that it is hard for an adversary to recover it. So as an example, let's see what happens when you have G equals 2, A equals 43, and B equals 21. So G to the 43 mod P, so G to the 43 mod P equals 86, and that would be capital A, while G to the 21 mod P is equal to 89, which equals B. Now A to the B mod P is, so if A is 40 and 86 to the 21 mod P is 8, and B to the A mod P, that is 89 raised to the 43 mod P, and that also is 8, and that is the shared secret between Alice and Bob. Now, shortly after the first publication of the Diffie-Hellman protocol, Rivas, Shamir, and Eldman proposed an example of a public key encryption scheme. Here, the idea is that there is a public key available to everybody, and it allows the encryption of a plain text. At the same time, decryption is only accessible to those who have the private key. Now, in theory, it means that any plain text can be encrypted by a person with a public key. In practice, usually it is used pretty much in the same fashion as the key exchange protocol, meaning that it is used for encrypting the key to a block cipher, for example, and then establish a communication entirely via private key cryptography. So, but in theory, the reason for not using it to encrypt larger messages is simply efficiency. So here is how the RSA encryption scheme works. So we need to use a trapdoor function, meaning that it needs to be a function that allows to go one way, but only going backward with the knowledge of a secret, which is usually used called a trapdoor. So the public parameters are an integer n, and an exponent e that is coprimed to a phi of n, and the private parameters are phi of n and the inverse of e mod phi of n. Note that that operation is easy as long as you know phi of n. Now here's how you encrypt a message. It is simply raising m to the power e reduced mod n. How can we possibly recover m simply from the ciphertext and the exponent? Well, we use the fact that any x coprimed to n raised to the power phi of n is congruent to 1 mod n. And which means is if you raise the ciphertext to the power d, this is congruent to m to the ed mod n, and you can substitute ed by 1 plus a multiple phi of n because they're assumed to be inverse modulo phi of n, and you can break that product, and it's m multiplied by something raised to the power phi of n, which is essentially 1 and which disappears from the equation. In practice, the best choice of n is a product of 2 primes, and there are restrictions for how you can choose those primes so that the crypto system is secure. And in this case, phi of n is the product of p minus 1 and q minus 1, and there is no in general, there's no efficient way to find the value phi of n apart from essentially factoring n. So let's see on an example how this works. So here phi of n is phi of n is 3120. Okay, and from phi of n is easy to calculate the inverse of e, which is in this case 2753. Okay, now let's say m equals 2. Well, we'll see that m to the e mod n, which is the ciphertext, well, this equals 1752, and you can verify that c to the d mod n, which is 1752 raised to the 2753 mod n, that lands back on 2. Now, the previous example of the use of the RSA primitive for public key encryption, given how we use it in real life, might not seem such a novelty, considering that we already knew since Diffie-Hellman how to create a private key, a shared private key through an unsecure communication channel. And since most of the time RSA encryption is used to ensure that there's a shared secret between two parties, it seems that it is not, we could basically stick to Diffie-Hellman. But the RSA primitive also allows what is called digital signature. And basically what it means is it's a signature scheme that allows only the person with the private key to sign a document, but everybody can verify the signature using the public key. And that is very important in a lot of situations involving cybersecurity. In particular, certificates when you browse the internet, or for example, transactions on the blockchain with cryptocurrencies. So usually what happens is documents are first hashed before being signed, and that is essentially for efficiency purposes, of course, and because we assume that the hash functions that we're using are collision resistant. So the hash that is created is signed with the private key, and together a signature is only, of course, only makes sense when it comes with the document. And then the verification happens by essentially comparing the hash value and the application, the verification algorithm that takes the signature and the public key and must return essentially the same hash value. So when a verifier compares those two values, they agree on the authenticity of the document if it checks. So with RSA, we can, just the same way we could encrypt, we can sign by using the same property that relies on Fermat's little theorem. So here, the signature, the operation consistent signing, is the exact opposite as the encryption, meaning that we raise this time the message to the power of the private exponent, so m to the d mod n. And to verify a signature given the public exponent message, where we use the same properties as before, and we raise the signature to the power of the public exponent, and that, for the same reason as before, should equal m. And the verification protocol then consists in calculating the s to the e mod n and verify that it equals the message. So of course, again, the verification protocol takes both the signature and the message and the public key as input, and the output, of course, is whether or not it is a legitimate signature. So again, here we have the same value phi of n as before, but our signature, if d is as before 2753, and m is 2, then the signature of m and d is m to the d mod n, which equals 1027. When you raise the signature to the e, you retrieve 2, and that operation tells you that the signature was legitimate. And as a hands-on activity, I encourage you guys to try with the virtual machine the OpenSSL command lines that allow you to create RSA keys to encrypt and decrypt with RSA, and to sign and verify signatures with RSA. Thank you very much.